Yes, good morning, everyone. For those of you who don't know me, my name is Kaustubh Rajwade. I am a researcher based at the University of Oxford. So this morning, I'll be talking to you about the Meer trap project. So I'll basically first describe what this project is, and then end with some of the science that has been happening since we went operational about 4 to 5 years ago. So since last week, we have been hearing a lot about fast radio bursts. These are cosmological flashes, radio flashes that we see from all over the sky. And there's a lot of scientific interest in two things. One, trying to figure out what they are, because that's kind of probing some extreme physics that we really cannot manage to possibly do in labs on Earth. And also to try and realize their potential as cosmological probes, because we know they are cosmological. The question is that whether we can really use them to answer some key outstanding questions in cosmology. Since the field kind of kickstarted about, it's almost coming to 2 decades now, there's still some open questions, right? For example, in terms of figuring out the emission mechanisms, there's still a bit of debate on what's happening, right? Are the FRBs coming from the magnetosphere of a very energetic compact object, or are they coming from a bit far away from the compact object, whereby you have a kind of a flare that's kind of shocking the ISM, and that's what's causing the emission of these FRBs. As far as the application is concerned, again, like if one of the key applications we can see is that we're trying to map out, the baryons the distribution of baryons in the universe. And so it's quite important that we not only detect FRBs, but localize them very, very accurately so that we can identify their host galaxies and also then try to disentangle the different contributions of the different components of the cosmos in terms of like the intergalactic medium, the host galaxy ISM, and Milky Way, and so on, to really kind of literally weigh the universe. And so what we need is that we need to continue monitoring the sky for these things. We need to continue discovering FRBs, and we need to continue localize them. So then the next obvious question is then why not do it with basically all radio facilities that are available across the globe? And so that's what we did, right? So Meer trap is a commensal real-time FRB, the fast transient detection instrument, that's been deployed at the Meerkat radio telescope. So for those of you who don't know, Meerkat is a 64-dish radio interferometer. Each dish is about 13.5 meters in size. It's located in the Karoo Desert in South Africa in the Northern Cape. Excellent RFI conditions. You tend to get a very clean band. And the idea is that we are observing commensally. So what I mean by that is that Meerkat has basically the time on the telescope is allocated to different science goals. And while the telescope is observing, we're using the same data to look for fast radio transients in real time using a compute cluster. So this is the collaboration. So the Meer trap project is PI'd by Ben Stappers, is based in University of Manchester. And we have a lot of collaborators from the Max Planck Institute in Bonn, and of course, University of Oxford and the Oxford E-Research Center. But also, of course, none of this would have been possible without the help of, firstly, NCRAO, because they've supported us immensely during our commissioning observations, earlier in this decade when we just deployed the instrument. And of course, our good friends from F4 who help us to, follow up these FRBs at optical wavelengths to identify host galaxies and estimate redshifts and so on. So just a shout out to all these lovely people. So again, I spoke about commensal observing. So one of the key benefits of commensal observing is that you don't have to keep applying for observing time at the telescope to do your science. And so you're using the same data stream that's being used by different science cases or science proposals to look for FRB. So we basically have agreements with pretty much all these proposals that I list here. These are large survey projects that were allocated a significant amount of time at Meerkat when it became operational in 2018. And you can see that by the time all the large survey projects end, we're going to end up with almost 20,000 hours of observing time on Sky with Meerkat to look for FRB. So that's a big opportunity to do a lot of interesting science. So I'm just going to go through some of the key observing modes of Meerkat. So the first and foremost is the incoherent mode. So what we do is we are basically detecting power from every antenna that's observing, and then we're just summing them up together. And so that basically creates a single beam that's looking at the entire primary field, or the size of the entire primary field of view of the telescope. But at the cost, you get this large field of view at the cost of sensitivity because you're not coherently adding these signals from the antennas. And so it's kind of equivalent to doing a survey by a single 64-meter dish, similar to the Parkes or the Murray-Yang radio telescope in Australia. But you end up having a rough field of view of 1 square degrees at 1.3 gigahertz. Then, of course, the next mode is the coherent mode, so whereby you can kind of fill up your primary field of view with much smaller but way more sensitive beams, which are the coherent beams, in which case, as the name suggests, you're actually phasing up the array in some sense. So you're actually adding the signals coherently by keeping the phase information. So it does mean that you get a larger sensitivity compared to the incoherent addition, but it also means that you lose a bit of the field of view. So which means that you need a lot more smaller coherent beams to fill up the same field of view if you want to do a much more sensitive search. Now, of course, because of computational limitations, we cannot fill up the whole primary field of view with coherent beams, but we get a rough field of view of about 0.4 square degrees at 1.3 gigahertz with this mode. But it does mean that within that region, we have a much, much higher sensitivity towards FRB, and which is comparable to like doing a survey with a 100-meter dish, which is quite good. And lastly, we have the transient buffer mode. So I think we have spoken about this last week as well, whereby if the real-time system detects an FRB, it sends out a trigger which saves all the channelized complex voltages for every single antenna at the time of the burst, right? And now the advantage of that is that you can actually then use these channelized voltages to make visibilities, use that to make radio images at a very, very high time resolution, and actually detect that FRB in these images and get a localization out to about an arc second or less. And so then that precision is kind of required if you want to do optical follow-up then to identify the host galaxies. And so, yeah, so those are the three kind of key things for the survey. I'm not gonna go through the details here, but the key thing is that, yeah, we're roughly looking for FRBs in the range for dispersion measures ranging from 0 to about 5,000. Yeah, with anywhere from less than a millisecond to a few hundred milliseconds. I mean, this number here, I mean, this was kind of increased later once we started to find some of these really wide and really interesting long period sources. And so you want to try to kind of cover that parameter space a little bit more so that not you're completely biased against that population. Yeah, so we're using this C++ based real-time single pulse search pipeline called Cheetah. It's basically a prototype pipeline for the current software stack that is being developed for the square kilometer array as of now. And then we're using a machine learning based classifier. So last week we mostly talked about a CNN called Fetch, which is widely used to identify FRBs and other radio transients in telescope data. We are using a similar machine learning classifier called FRB-ID, which is a slight variant of Fetch, and that's what's being used for any candidates that come out of the single pulse search pipeline. Yeah, so the hardware was actually installed in the Karoo Array processing building on site back in 2018. So this is how it looks like. So we have 65 compute nodes and a head node. Each node processes 12 coherent beams. So we can search for FRBs in 768 coherent beams in real time as of at the moment. You can, of course, increase the number of beams and stuff, but then it's at the expense of probably reduced bandwidth or reduced time resolution and so on. So that's a choice you have to make because you only have limited amount of compute available at any given moment. Yeah, that's just, I mean, honestly, I mean, I used to show this slide like maybe 5 years ago pretty proudly, but when you look at NVIDIA G1080 Ti's these days, it's pretty outdated GPUs. Given what's available in the market at the moment. But it still does the job for us. And more importantly, we do have some spare GPUs now because every now and then, one of your GPUs, gets fried because of whatever reason. So it's quite important to keep a few. Just from experience, do remember that when you're building a new instrument. The transient buffer system. So as I mentioned before, in the event that the real-time system detects an FRB. So the way it's built right now is that we have these two compute or clusters. One is the filter bank beamformer. So that's where the beamforming happens. So data comes through from the telescope. You get the beamformer, makes these hundreds of beams, which are kind of transferred to the actual Meer trap system through the network. This is where the search is happening. And then if you are getting a detection, it basically sends out a trigger back to the beamformer, and the beamformer immediately freezes the channelized voltages that it's getting from the telescope. Now, if you assume that you always want to save enough data that you're covering or basically that spans the entire duration of your FRB, dispersion is a problem, right? I mean, depending on the DM, you would have, so the amount of data that you will save will depend on how dispersed your FRB is. And so that would mean that if you start finding FRBs at higher and higher DMs, you're going to save a lot of data. And these data can be pretty hefty, right? We're talking about like almost like 10, hundreds of GBs for like, a few seconds of data. So that's kind of not necessarily sustainable if you're getting a lot of triggers because of RFI or various other reasons, and you have to keep cleaning up the disk so that you don't miss new triggers. And so what we did was that we basically built a system where when we trigger and when we're saving the data, we actually cut across or account for the dispersion sweep of the FRB. And so because the value of the DM and all the necessary metadata is already, the real-time pipeline already has that. And so all of that information is actually sent to the program that's actually doing the triggering and freezing the data voltages. And so you can actually do that. And what that means is that regardless of the dispersion measure of your FRB, you're always going to save the same amount of data per trigger. And so what we do is that we save about 300 milliseconds of data at the time of the FRB for every single trigger. And again, it does not only allows you to localize, but it also gives you polarization information, right? And so you can do high time resolution studies and of any FRBs you detect, and also study the spectro-temporal polarimetric properties. So I'll just go through some of the key, some interesting functionalities that you get with kind of a flexible beamforming system on conventional backends. So I mentioned that, so this is an example of like a tile of coherent beams that you can make. But we are kind of flexible in terms of where we can put these tiles in the primary field of view, and also how much overlap do you want between your coherent beams, right? Because you can say that, okay, I can spread out my coherent beams in the primary field of view, which means that it'll cover a bit more sky, but you also kind of risk FRBs falling in these gaps between the coherent beams and where they won't be very sensitive, so you might miss out a few events. On the other hand, you don't want to overlap them too much because then you're just covering a very, very small fraction of the sky. Even though it's very sensitive, but then it's a very small field. So you still lose kind of FRBs, or your rate of discovery will still be low. So you want to play around with that, and which is what I'm showing here, right? I mean, it shows you different tiles and how they'll look like with different kinds of overlaps between these beams. And so you want to go with something that optimizes for sensitivity and the field of view. So typically what we realized is that if we have an overlap of 25%, meaning adjacent coherent beams are overlapping at the 25% power level. That's what basically would give us the best kind of discovery rate for our searches. Similarly, when I talked about flexible tiling, we actually can make separate coherent beam tiles in different locations of the primary field of view, which means that if you have interesting known sources in the sky, right? For example, you're observing something and then you realize, oh, there's an interesting neutron star right now in the primary field of view. Oh, there's a well-known rotating radio transient that I would like to look at. You can basically just on the fly create a set of tiles or just even one beam and just point to that source and keep following it up while that source is in your field. And that's just an example. During commissioning, that's what we did. We placed 3 separate tiles on 3 3 pulsars, and we got detection, simultaneously detected all three of them within single observation. So it's very interesting, especially for monitoring and follow-up observing campaigns of fast transients. I think we've also spoken at length about optical follow-up for host galaxies, but also I think if we want to figure out what are the progenitor models for FRBs, I think it's quite crucial that we detect some kind of a multi-wavelength counterpart, right? I mean, when we saw this FRB-like burst from SGR 1935 almost 5 years ago, there was a contemporaneous high-energy burst that was seen with this FRB-like pulse. So we do believe that there are these high-energy components to these things, but we're just not sensitive enough at the moment. So there have also been models out there that predict that there should be some kind of a prompt optical emission there as well. Not just that, right? I mean, you don't want to look. I mean, that's just as far as the prompt emission is concerned. But also you want to try to look for multi-wavelength counterparts after the event has occurred. For example, something like an optical afterglow, because that will kind of constrain the progenitor models. Because if you see an optical afterglow after an event, an FRB-like event, that kind of gives support to models like cataclysmic models, like possibly some of these FRBs are coming from some of these violent explosions that happen in the universe. And so with Meerkat, we have the opportunity to get this contemporaneous optical coverage. So Meerkat is a 65 centimeter fully robotic telescope that's built in Sutherland in South Africa. And so on a best effort basis, it always tries to co-point with Meerkat during all nighttime observations. So what that means is that if we have an FRB in the nighttime, we're almost guaranteed optical coverage with this telescope. I think it's a bit optimistic, honestly, because we've had some issues. I mean, there have been for various reasons, we've not managed to get optical coverage for a lot of our FRBs, but recently we finally managed to do that. We were almost contemporaneous. I think we were, because of some of in the dead time between different observations, we were off by 3 seconds, I think, from the event of the actual FRB. But that still means we can get some nice constraints on like the optical magnitude from potential afterglow that you could get from these FRBs. So now the last bit, I'm just going to quickly talk about some of the science that we've been doing over the last 4 years. So we are a commensal project, and so Meerkat looks at a lot of pulsars, and which means that we get a lot of galactic plane time from Meerkat. And so that does mean that we end up seeing a lot of interesting single radio pulses from neutron stars in our galaxy. And so far we have discovered about more than 110 of these things, most of them very sporadic, rotating radio transients type sources. But we've also seen some very interesting pulsars, like especially the slower pulsars, right? Pulsars with much slower rotation periods than what we typically find. So one is the discovery of the 76-second pulsar, discovered back in 2022, I believe. Yeah, so again, I said we have increased the width parameter space in our searches just because we found this thing, right? I mean, it kind of made us realize that we're probably losing a lot of these wide single radio pulses because we're just not searching for wide enough pulses in our real-time system. And another one, very interesting one, was that recently we found was a pulsar which had a spin period of 17 seconds. So we're starting to really find these very slowly rotating neutron stars and trying to fill up that kind of, I would say, middle to bottom right kind of space in the PP dot pulsar parameter space. And then we also end up finding things like this, right? I mean, this source, we saw it in a single 20-minute observation. It was pretty much booming, extremely bright, saw every single radio pulse from it, got a period, roughly 10 seconds. And this field is observed very frequently by Meerkat, like once every 2 weeks or so. And we have never seen this source over the last 3 years after that. We saw it once in one 20-minute observation, and then we've never seen it again. And so this kind of begs the question, how many of these extremely intermittent and extremely sporadic radio emitting neutron stars are out there that we're completely missing because we just lack that continuous wide field radio coverage of the sky. So the point I'm trying to make here is that I think there's a big need for high cadence, wide field of view radio surveys to exactly kind of remove these select observational biases that we have and try to find a lot more of these interesting objects there. Coming to FRBs, we so far found more than 80 FRBs. Roughly 30% of them we have triggered on and have localized to arcsecond precision. And the reason for such a low number is that initially the transient buffer pipeline was not fully operational. And also sometimes we do end up missing a trigger depending on the latency between sending the trigger and when the FRB happened. Because sometimes if the RFI environment is bad, we do slow down our pipeline. It does slow down our pipelines, and that leads to us missing the storing of the voltage data completely. But very interestingly, given that Meerkat is so sensitive, we find these very high DM FRBs quite frequently. Very recently, just kind of highlighting one of the key results that have come out very recently, we found this FRB at a DM of, actually that's not correct, it was 2642 instead of 2462. We applied for some DDT time with JWST, and actually, so this is I believe it's a NIRCam image of the field. And you can see that we managed to find this very, very faint source, which we definitely believe is the host galaxy for this FRB. And the redshift we estimate for this is 2.15. So this is the first FRB as of now that we know has a redshift of more than 2. So we are starting to find these very, very far away FRBs thanks to the incredible sensitivity of Meerkat. And of course, we have just showing you some interesting kind of dynamic spectra for some of these FRBs. And this is just showing you the power of the transient buffer, because both these sources were seen as single Gaussian peaks in our real-time system. It's only because we had the transient buffer data that we could go down to high time resolutions, right? We're talking resolution of about 4 microseconds here. And suddenly that FRB turns into something weird, into something that has a weird shape with multiple components that show up at different kind of frequency Cs in the dynamic spectrum. And then, yeah, of course, as I mentioned, that we're building this with Meerkat, a sample of FRBs at higher DMs, and which means that if you put them on this McQuart relation that we spoke about last week, which tells you about what the rough redshift would be for an FRB given the extragalactic DM that you see from it or that you measure. And then if you have a big sample that you can localize well enough, then you can kind of use that to kind of constrain this relationship at these higher redshifts. And the only way you can do that is by finding these things with very sensitive radio telescopes. And Meerkat is going to be probably very crucial until these next generation telescopes show up to kind of fill up this kind of parameter space here in the McQuart relation. Then recently we found this very interesting galactic source, single coherent radio burst from it, which was localized to a known thermal X-ray neutron star. which is not known to be radio loud. It basically belongs to a subclass of neutron stars called X-DINs, or X-ray dim isolated neutron stars. People have always spoken about the relationship between X-DINs and radio pulsars. I'm almost done, it's my last slide. Yeah, for the first time, it's showing us maybe we have found this missing link kind of transitioning source where showing us an evolutionary path between these different subpopulations of neutron stars. And lastly, we have also started finding repeating FRBs. As we know, it's a very small fraction of FRBs that we see. Meerkat so far has found 2, and again, just an example of like showing some super interesting emission features. So I think I'm just going to end up with my summary. I hope that I have kind of driven home the point that Meerkat is an excellent radio telescope for doing FRB science, and we're starting to find these very interesting, very far away FRBs, which we're starting to finally, start using FRBs as some very interesting cosmological probes. And if we combine this data with all the other radio telescopes like DSA and ASCAP, I think, the future is looking very bright. So I think I'll end there now. Thank you.
Thanks, Kaustubh. Very interesting talk indeed. Questions for Kaustubh?
Hey, thanks, Kaustubh, for the interesting talk. So one thing is, so you said that you are increasing the population of FRBs having high DM. So do you intrinsically find those to be more faint or having less fluence?
Not. I can't say, I don't think I can comment on that at the moment, because the problem is that we have found these FRBs with high DM. It doesn't necessarily mean that we have the exact distance to them. So until we actually estimate the redshift, it's only then that I can actually get a luminosity for them, and only then I can comment. So the problem right now is that we have a couple of these sources. They're definitely not, they're definitely on the higher luminosity end based on the redshift that we have. I won't say that they're like something crazy bright. It's definitely consistent with the population. But a majority of these high DM FRBs, we're still struggling with A, identifying the host, and B, getting a redshift for those hosts, just because of the limitations in optical telescope capabilities and also the limited resources that are available. But yeah, definitely something to look at. Thanks.
Hi, Vikram here. So last slide, it seems like FRBs found by DSA 110 are biased towards the higher DM at low redshift. Why is that? And then another question is like, the FRB that you showed in the previous slide is already there, right? The redshift 2.7 or something? Or that's
this one?
Yeah.
Yeah, so
that's the JWST one.
Yeah, so okay, so this, okay, I guess the disclaimer is that this plot is a little bit outdated, and some clarification. So these lines, this is not a fit. It's a model prediction based on the Planck results for different cosmological parameters.
The dashed line.
Yeah, the dashed line, and also these are just the model uncertainties. So you get a bit of a scatter basically. So the expected scatter that goes increases with your high redshift. These yellow points are the Meerkat ones, and the reason they're on the line is because we still don't have an exact redshift for them. So it is just based on if this is the DM, this is the, and that's why you have these error bars that kind of span across your posterior distribution. The DSA ones, yes, those have redshifts, and there's a paper by Liam Connor where he's actually tried to show that by doing modeling that this curve is kind of slightly tilted upwards than what you see from the predictions. And yeah, so that's what it is. So this is not a fit.
So your FRB, what would be the redshift?
So this one now is over basically like here. It's a kind of an outlier here as well.
And even the DM value is smaller than 2,400, right? Or DM is.
Yeah, I mean, yeah, I think, yeah, it's like here somewhere.
Okay.
Yeah. Yeah.
Thanks.
Yeah.
Kaustubh, thank you for the talk. So I was just wanting to know whether Meerkat allows commensal observations of these, and how long you think these observations can go in as the SK is coming in as well?
Well, yeah, I mean, we would like for them to keep us online for as long as they can until Meerkat is fully integrated in the SK. The problem is that Meerkat is building a new correlator for Meerkat Plus, which is 15 more dishes being added to the 64 dish array. And so they have a completely new network for that, which we're not connected to. So we'll still continue observing with the 64 dishes when Meerkat Plus comes online. So just hoping that the old network still keeps going strong, because you never, things like network issues is a big problem, especially with old hardware. So fingers crossed that we can still continue all the way up to, SK mid. But yeah, I really don't have any solid predictions as to when and for how long we can go commensal. Yeah.
Hello. Hi, Kaustubh. So your current 80 detections, how much roughly on sky time they have resulted from?
I don't know the number on the top of my head.
And are there expectations of some number from your eventual?
So typically our rough rate of discovery, if typically Meerkat is like about 70-ish% efficient in observing. So in a year, roughly 70% of the time it's on sky. And if you assume that, then our rough detection rate is like once a month or something, 1 FRB per month. So it's roughly consistent, but there are so many variables in that. It's a very ballpark number.
But there's some expectations on numbers.
It is very close to the expectations, yeah. Okay. Yeah. On the lower side, it's not higher, but still consistent with the error bars, I would say.
Thank you.
Any questions from the online participants? Any further questions from the audience here? Comments? Last question.
Do you have a new record for Z of 3? Is there a point at?
No, not as of now, no. We don't. I mean, who knows? I mean, we have an FRB that has a DM of 2800, but I have no idea. Like, we haven't done any optical follow-up for that, so really can't comment on what the redshift would be for that. Yeah.
All right. On that note, let's thank Kaustubh